Hello and good evening. My name is Joan Concannon and I'm the University of York's Director of External Relations and the Director of the York Festival of Ideas. A very warm welcome to you all and I hope you're all safe and well. And an especially warm welcome to this evening's speaker, Dr Kate Lancaster. This event is part of the University of York's Open Lecture Programme. We are really excited that you're all joining us here this evening. Do please feel free to promote this event far and wide by connecting up with us on Twitter at UOY events and use the hashtags #YorkIdeas and #UOYCommunity. A few technical notes before we start. If you're watching live, you can ask questions using the Q&A button on your screen. This is available throughout the talk, so questions can be asked at any time. Should you have technical issues such as a loss of Wi-Fi, you can rejoin the event using the original link. Please also remember that today's event is being recorded, so you'll be able to watch it again and share it with your friends. Public engagement is a core part of the University of York's mission. We want to ensure that as many people as possible understand the relevance, importance, and impact of research on our everyday lives. The university's founding principles in 1963 were very much about demonstrating how a new university can be for public good. I don't think there has ever been a more important time to ensure that universities continue to deliver public good and that through our public engagement, we ensure we can foster an understanding of our social purpose. I'd like now to introduce our guest speaker, Dr. Kate Lancaster. The title of Kate's talk is It Possible to Build a Star on Earth? Trying to recreate the energy sources of the stars, nuclear fusion on Earth presents huge challenges in physics and engineering. The benefits of nuclear fusion, if successful, are an almost limitless clean energy source. There are many challenges associated with keeping matter at 150 million degrees trapped inside a reactor without touching it. This talk is the story of how, in the absence of a lab the size of a star, we're attempting to make fusion into an energy source for the future. Just a tiny, insignificant topic. Kate is an experimental plasma physicist with expertise in inertial fusion energy and the ultra-intense laser plasma interactions, industrial engagement, knowledge transfer, teaching, and science communication, where she regularly enthuses thousands of children about the joys of physics. She was awarded a PhD in Advanced Fast Ignition Studies, Laser-Driven Fusion by Imperial College London, before working at the Central Laser Facility at the Rutherford Appleton Laboratory. Her background is in laser plasma fusion, and she's now a lecturer at the York Plasma Institute here at the University of York. On Twitter, somewhat bizarrely known as @Dr Katie Pugh, she may explain, she describes herself as loving lasers, plasma, fusion, dancing, and cheese. So 2 out of those I share a common interest with. Over to you, Kate.
Thank you so much for that kind introduction. My Twitter handle, in fact, it was a nickname that my mother gave me when I was rather small. So she always used to call me Katie Poo. So that is why I have such a bizarre Twitter handle. So thanks, Joan, for the introduction. Okay, so this talk is about whether it's possible to build a star on Earth. And that seems like a rather grandiose thing to do. But in actual fact, what we're trying to do is create a sustainable clean energy source on Earth. So we're not just like mucking about trying to waste taxpayers' money building these miniature stars. Actually, there's going to be a real impact if we get it right. And this talk is the story, like myself, of trying to make nuclear fusion a reality so that we can have clean energy for the future. So with that, I shall start. I took this picture out of the hotel room that I was staying in Yokohama. And the reason that I use this as my first slide is because I really feel like it emphasizes our kind of modern problem in that we're energy addicts. You can see just this sprawling kind of mass of lights out ahead of you. Basically, as our population grows and our demand for energy, because our quality of life is increasing, also grows, but that our ability to get energy from current sources, to find some method of generating energy that's clean and safe, that is actually going to give us the quantities of energy that we actually require. And at the moment, if we don't do something about it, then the energy that we need is going to far outstrip the energy that we actually have access to. So basically, you're all going to be panicking right now, and it sounds a bit of a grim future, but in actual fact, hopefully this talk will give you some reassurance that we will be able to try and find a solution to this energy problem. So if we consider, if we're all scientists and engineers, and we have to design the energy source from scratch, a perfect energy source, what would we want it to do? Could you advance the slide? And again. So there are a number of things that we really need a perfect energy source to be able to deliver. So we want it to be clean. Our current energy sources, some of them are polluting to the environment. They actually kill people through pollution. And we want them to be clean for the environment going forward, because we are facing both pollution and climate crisis. So we do need to produce a sustainable energy source going forward that isn't going to harm our environment. And I mentioned the word sustainable. And we need the energy source to be almost inexhaustible. We want this clean energy source to last for a very, very long time. Otherwise, it's pointless putting all of this energy in, developing this energy source, and then it to run out. So we need the fuel to be almost limitless. It needs to be safe, because basically this energy source is going to be in our locale. And that's really then why we need it to be safe, because if we're around it and we're living around it, we don't want it to blow up on our doorstep. That's pretty undesirable. And we also need it to be reliable. So if you think about if you're watching Coronation Street and you put your kettle on, and so there's the break in the middle of Coronation Street and everybody rushes to put their kettle on and there's a big spike in demand, then the way we normally deal with that is you bring a power station on to cope with the demand and then take it off again. So whatever energy source that we deliver has to be turn off and onable, basically. We need to be able to have it subject to demand. Now I've put cheap here with a question mark, because we possibly are through the era of cheap energy. It would be great if it was cheap, so there was good energy access at a manageable level for everyone, which it should be, but it's never going to be cheaper than what we have now, I don't think. So it turns out there is an energy source that fulfills all of those requirements. And if we look out into our dear universe, we can see all of the stars in front of us. And those stars are powered by nuclear fusion, which is basically when two atoms come together and produce energy. Now, the stars basically are turning hydrogen into helium and then into heavier elements. And so it turns out all the atoms that make up our bodies and everything around us were forged in the center of stars and were a direct result of nuclear fusion. So nuclear fusion was absolutely fundamental to life on Earth, but it also might provide us with a really clean and attractive energy source. So somehow we need to recreate what's happening inside the stars on Earth. So how might we go about doing that? So we need to look then in a bit more detail about the nuclear reactions that we are trying to achieve. So the sun and the stars, they turn hydrogen into helium through a fusion reaction. And we're going to do the same thing, basically. So we're going to use two types of hydrogen, so deuterium and tritium. So deuterium is present in seawater in really large amounts. So for every 6,000 hydrogens, there's one deuterium. So there's absolutely tons of it in the sea. However, tritium isn't naturally occurring. So for every 10 to the 17 hydrogens, there's one tritium. So that's 1 and 17 zeros, okay? So that basically means tritium is not naturally occurring, but we will try to make it. So we'll come back to that. So I'll come back to how we're going to actually generate the tritium. So what we need to do is give the deuterium and tritium lots of energy, then they fuse together, and then what you produce is the helium nucleus, which is otherwise known as the alpha particle, and a neutron. And the neutron carries away most of the kinetic or moving energy of this interaction. And it's the neutron that we want to capture. So how do we get energy out of this reaction? Well, the equation that I have on the slide there is the most famous equation in the world. It's E equals mc squared, which was a result of Einstein's great thinking. So that is energy equals mass times the speed of light squared. Now, Einstein said, quite rightly, that the speed of light is constant wherever you are and whatever reference frame you're sitting in. So for the purposes of this equation, if c is a constant, then that means that energy and mass are somehow interchangeable, and we can turn one into the other. So what does that mean for us in terms of getting energy out of fusion? So if we take deuterium and tritium and we weigh those particles and add those masses together, and then we interact them together, and then we get our helium and a neutron and we weigh those particles and add those together, what you'll find is there's a mass loss between what we had before and what we have now. And if we take that tiny little value of mass and times it by c squared is an absolutely huge number, by the way, then we get absolutely enormous quantities of energy. So it's a very efficient way of producing energy, but how do we get that? How do we generate that tritium? Well, it's the neutron that we really need, because what we're going to do is surround the reactor with lithium, which is also very abundant, and the lithium will capture the neutron and make tritium. So whilst we're doing these reactions and producing energy, we can also capture the neutrons and make tritium as well. So it sounds very neat. We don't know if we can do it in sufficient quantities yet, but that's basically the idea. So that's how we're going to try and get all of this unlimited energy. So this is a really, really efficient way of getting energy. You don't need very much fuel to get large amounts of energy. So for example, 40 tons of coal, if you burn that, that is the same amount of energy as you would get from fusion between the deuterium that's contained in half a bar full of seawater and the lithium in a laptop battery. So that is a really small amount of fuel. But there's something even more profound about that half a bar full of seawater and the lithium in a laptop battery. That's basically one of your lifetime's energy needs solved. One of your lifetime. So it's about 30 years worth of energy that you would get just from that small amount of fuel. So this is why scientists have been spending decades trying to get fusion right, because it is such an attractive and efficient energy source. Now, there are more advantages to fusion, not just this amazing efficiency. So if we think about the kind of nuclear power stations that we have now, they're based on something called fission, which is where we take a big atom and split it into smaller atoms, which also releases energy. But the problem here is it produces lots of radioactive waste. Now, personally, I'm not opposed to fission. I think it's really important as part of the energy jigsaw. But nonetheless, it does produce a lot of radioactive waste, and it's really unfortunate moving forward because it is a very big burden on future generations. Now, with fusion, we don't produce long-lived radioactive waste. We just produce helium and a neutron, and so there's none of this long-lived burden. However, neutrons do go into the surrounding reactor material, and that does create some radioactive isotopes in the reactor walls, but they're not long-lived and they're not a big burden for future. So it's actually a really, really safe thing. Now, talking about safety, this is a picture of Chernobyl at the far right here. And that was a big nuclear accident in Russia in the 80s. Now, the thing about fission, that was a fission power station. The thing about fission is you have all the fuel that you need present at all times in the reactor, and you have to carefully moderate the reactions, otherwise they'll run away with you. Now, the thing about fusion is this won't happen because you have an extremely small amount of fuel present at any time. And it's extremely easy to make fusion not work. I mean, we've been doing that for the last 60 years, right? So, but basically, fusion is inherently safe. You can switch a fusion reactor off and it will stop immediately. whereas this is not the case in a fission reactor. And last but not least, there are no CO2 emissions, so it won't be contributing to climate change and pollution in the atmosphere and so forth. So overall, I think it's an extremely ideal energy source. So it's kind of the holy grail of physics. So let's get on to the crux of how on earth we're going to take a star and make it in miniature on Earth. All right. So in order to do what a star does, we're going to have to be able to get matter, heat it up to 10 times hotter than the center of the sun. So the center of the sun is about 10 to 15 million degrees Kelvin, centigrade, whatever you want. We need to go 10 times hotter than that just to increase the number of reactions that we have. So 150 million degrees. Now that means the matter is really hot, and so it will start to expand. So in order for the particles to interact with each other, we have to keep them together in order that these particles will interact and fuse. So the task that we have before us is that we have to keep matter at 150 million degrees Kelvin together without touching it. And so you can start to see why this is extremely difficult. Now, the other thing is, when you heat matter to high temperatures, something really unusual happens with the state of matter. So if you remember at school, when you learnt about states of matter, you have your solids, your liquids, and your gases. Now, if you add energy even further to the gas, for example, then what happens is the atoms kind of start to fall apart. So if you think about what an atom looks like, it's the nucleus in the middle with the electrons kind of whizzing around the outside. Now, it turns out that some of those electrons can gain energy and escape the atom. So what you're left with is a kind of soup of charged particles, so positively charged nuclei and negatively charged electrons kind of whizzing around, so ions and electrons kind of whizzing around together in a soup. And that soup of charged particles is the fourth state of matter, which is called plasma. And that's why I'm a plasma physicist, because we have to study this plasma in order to know how to make fusion work. So not only have we to, hold this matter together at 150 million degrees Kelvin, we also have plasma to deal with as well. And that's kind of like the stroppy teenager of the states of matter world. So the sun is pretty good at doing this. The sun keeps itself together because it's massive, so it has a gravitational field. But we don't have a lab the size of a star on Earth. So we're going to have to do something a bit more cunning in order to make fusion work on Earth. Now, I think this kind of sums it up really nicely. It's a quote by a guy called Sebastian Balibar, who's a really senior guy at the CNRS, which is a big research organization in France, responsible for the next step of fusion, which is a project called Eita, which I'm going to talk about a bit later. So he said, we will say that we will put the sun into a box. The idea is pretty. The problem is we don't know how to make the box. So I love that quote. It's a little bit disingenuous because I think that we do have a good idea of how to make the box. It's just we haven't done it properly yet. Right, so how on earth do we get this box to work? Well, underlying it all is the physics of fusion. So we have three basic knobs that we can twiddle when we're doing fusion, okay? The first is temperature. How hot can you make the fuel? Now, this is pretty non-negotiable. You need to heat the fuel to pretty high temperatures because basically what you're trying to do is bring two charged particles together that are the same charge, the same sign of charge. And so they're really resisting each other. It's like trying to bring two poles of a magnet that are the same together. You can feel that resistance. And that's called the Coulomb barrier. So in order to overcome this so that the particles will fuse together, you need to heat them to really high temperatures. So the temperature part is non-negotiable. So what we're left with is kind of two knobs that we can play around with. So one is the density of particles that are present in our reactor, and the other is what we call the confinement time. So how long we can keep those particles together where they're producing net energy. So in reality, it's what we call the energy confinement time. So what you could do is take the approach that you could keep a moderate density of particles together for a long time, or you could keep, for example, a high density of particles together for a very, very short time, but just do it over and over again. And that kind of represents the two main ways in which we're trying to make fusion work on Earth. So we have two different approaches. So we've got one called magnetic confinement and one called inertial confinement. So they're all a bit of a mouthful, but I'll try and explain a little bit about what that means. So on the right-hand side, this magnetic confinement fusion that we've got here, it's basically based around a donut-shaped device called a tokamak. That's a Russian acronym, and don't ask me to say the Russian because I don't know Russian. But basically what we've got here is a big magnetic bottle. Now, as I said, plasma, we've got to deal with plasma before, and that's made up of a bunch of charged particles. And so it turns out we can manipulate charged particles to stay together without touching the walls of the vessel if we shape them in a special way with magnetic fields. So basically what this is a big donut-shaped device with specially shaped magnetic fields which essentially levitate the super hot plasma inside the center of the donut device and away from the walls. So you get an extremely large temperature gradient where in the center of the kind of donut shape cross-section, you get a really high temperature, you know, this 150 million degrees Kelvin, but out at the edges, especially out at the far edge, it cools down to like a few thousand degrees. The tokamak that you can see in the picture is actually a tokamak here in the UK. It's called the Joint European Torus. It's a European project based down in Oxfordshire at the Culham Science Centre. People from all over the world come to use this device. It's the most successful fusion device in the world. And it's a really amazing thing and a privilege that we have it here in the UK. Now, on to the inertial confinement side. So if we consider what magnetic confinement is, keeping the sort of moderate density of particles together for an indefinite period of time. Whereas on the other side, I said we could keep a really high density of particles together for a really short period of time. And that's effectively what inertial confinement fusion is. What we do is we take a tiny ball bearing sized pellet of deuterium and tritium, and we compress the hell out of it with 200 of maybe the world's most powerful lasers until it's really dense. And then eventually the compression and sort of kinetic energy of that, as the temperature and pressure raise inside the center of this little pellet, that movement is arrested, and that translates into heating of the fuel in the center. And then that raises the fuel to the 150 million degrees Kelvin that you need for fusion to occur. But you just do this over and over again. So it's kind of a nuclear fusion powered diesel engine, let's say. You compress it till it self-ignites and then keep doing it over and over. And so that kind of represents the two main approaches. Now, of course, there's a sort of infinite number of permutations of different types of fusion underneath this, but obviously I don't have till Christmas to tell you about all of those things, and I probably would. We just have to stick with this kind of basic notion of the two main ways of doing fusion. Also, we've got to consider what on earth would you make the outside of the box from? All right, so we've got two types of materials that we have to consider. So if you think about the tokamak, for example, this donut-shaped device, you've got materials on the inside that are facing this very, very hot plasma. So even though the walls are not being touched by the stuff that's hottest at the 150 million degrees Kelvin, because we're keeping it away from the walls, those walls are going to be subject to temperatures of, 1,000 or so degrees. So they have to withstand extreme temperatures. Like, it's kind of like landing a spaceship on the surface of the sun. It's really, really extreme stuff. Also, because we're producing lots and lots of neutrons, those neutrons can go in and they can undergo nuclear reactions with the material that the reactor is made out of and actually transmute them into other elements. And so then you have elements that you didn't intend to be present. They could be radioactive, for example. But also you've just got a kind of billiard ball effect where neutrons are kind of smashing into the atoms in the material and causing displacements. And then you get embrittlement and kind of the material properties of whatever the reactor is made of change. So I've put a kind of list of kind of candidate stuff for what is facing the inside of the tokamak and the plasma. So all sorts of stuff like tungsten, for example, is a really good candidate. It has a very, very high melting point. But then, of course, you need to make the outer box out of something. And this is where steels come in. So we look to our own dear steels that we've known for so many years, and steels, different types of special steels, will be extremely useful going forward, because that's what the whole thing is going to be made of. Where are we at now? So first of all, I'll talk about laser-driven fusion. You may have heard already that that is my interest, so it's not that I'm biased or anything, but this is really exciting. So what we have at the moment is something called the National Ignition Facility. This is the biggest laser ever built, and it's sitting in the Bay Area of California. So you might wonder what the sort of logic is of building an extremely sensitive laser optical device in a very earthquake-prone region, but you know, us physicists like a challenge, let's say. So as I said, this is the biggest laser system ever built, and I think personally, when I see it, the most beautiful laser system ever built as well. So it's been operating since about 2008, but it's really didn't ramp up until about 2010. So let me tell you what you're looking at here in the pictures. So on the top left, that is a vacuum chamber. And in the center of the vacuum chamber, where that bright light is a tiny ball-bearing sized pellet of deuterium and tritium. Now, you've got these lasers coming in, they're blue in color for physics reasons, which I won't go into. And those 196 beams that this facility has all come in and compress that tiny pellet to really high densities. Now, it all has to happen under vacuum. So there's this huge vacuum chamber that kind of looks like the Death Star from Star Wars. And it has to happen under vacuum because those lasers are just going to turn the air into plasma rather than the pellet, which is what you want to happen. So you have to evacuate all the air out of the chamber so that the lasers are directly interacting with the pellet and not just the air molecules. On the top right-hand side, you can see something that kind of looks like a factory or a water treatment plant. That's just some of the 192 beam tubes which take the laser beam into the target area. And then the bottom picture is just an aerial view of the whole facility, the whole National Ignition Facility. You can see it's 3 American football pitches in size. Now, we use American units of American football pitches, but of course, if it was in the UK, it'd probably be like, I don't know, Wembley stadiums or London buses or something. Now, this is an incredible system. It had an ignition campaign, i.e. it was trying to get more energy out than it put in. And that ignition campaign began in around 2010. Now, unfortunately, it's a science project, right? So we didn't actually get ignition, which is a real shame, but there's been absolutely loads of progress. And they've actually got to the point now where they've produced record-breaking numbers of neutrons. Well, why do we care about that? Well, for every fusion reaction we produce more neutrons. So for every fusion reaction we produce 1 neutron. So if we produce record-breaking numbers of neutrons, that means we've got loads of fusion reactions happening. And we really understand now some of the problems that happened, which meant that we didn't get net energy back in 2010 till 2012. So the physics at the moment is really exciting. And they're now at a real good point where only modest improvements in their parameter space will bring them closer and closer to this goal of net energy, i.e. more energy out than you put in. And what about the magnetic confinement fusion side? So as I said, that device that I showed you on the previous slide, this tokamak called JET, it's the most successful fusion experiment to date. And you can see from the nice cartoon there that it's probably quite old. JET started in around 1983, and you can see there a little person at the bottom. That's a standard size plasma physicist, so you can get an impression of the size of the device. Now, back in 1997, that device produced 60 megawatts of fusion power. So that's really impressive, but you might be thinking, well, what have you guys been doing since 1997? Well, this is the only plot, this is the only graph I've put in the talk, and this neatly summarizes why that is, right? So if you can see, along the bottom is time in seconds, and along the y-axis we've got fusion power in megawatts. Now that big blue peak that says JET 1997, that's this 16 megawatts of fusion power. But you can see the duration is only for a couple of seconds at the most. And this is because it's inherently unstable. There are instabilities going on, which mean you can't sustain this reactions for an indefinite amount of time. And certainly in the case of a tokamak, that's what we want to do, keep a moderate density of particles for a long time, getting net energy out. So lots of the research since then has been on what are these instabilities and how do we overcome them? Now, this makes it seem like there are instabilities in magnetic confinement fusion, but not in inertial. It was lots of instabilities in inertial confinement fusion that stopped it from working as well. So because we're dealing with plasma physics and hydro and all of this stuff, basically instabilities are the thing that bite you in the bottom with all plasma physics. So this is the thing that we always have to understand. So supposing we get any one of these methods to work, how on earth do we get the energy out? So I've based this on, well, I didn't draw this, but the person has based this on a tokamak, but it could easily be an inertial confinement fusion plant as well. So what we've got in the center here is the plasma doing its thing and producing fusion and then producing these neutrons. And these neutrons fly out carrying most of the energy of the reaction, and then they interact with the walls. And it encounters the lithium, which I said that we needed to generate tritium. So the lithium obviously has these two functions. Firstly, the neutrons will interact with the lithium and make tritium. That's great. But also, in doing so, that lithium is going to get hot. And then what we do? Well, we use that heat to heat water, to make steam, to drive turbines. So it's an extremely depressingly Victorian back end to something that's extremely space age. But this is the best way we know how to get the energy out, right? So don't break something that you don't that isn't broken, right? So overall, it seems like a neat cycle. But what do we do going forward? You probably heard the old adage, oh, you know, why is it always 30 years away? Blah blah blah. You know, breaking news. I'm bored too. Like, I want this to work. I want us to be able to get to fusion sooner. And now I'm going to tell you a bit about how we're going to do that, okay? So this is down the tokamak route, okay? So there's a next step device that's being built in the south of France, and it's called Eita. Now, if you remember rightly, I was talking about these instabilities inside the tokamak, which kind of cause it to fizzle out too quickly. So in order to, you can overcome these kind of energy losses by ramping up either ramping up the magnetic field or just making the reactor bigger. And Eita is the bigger approach, because if you can see right at the front there, a tiny little person in orange, that's a standard size plasma physicist. So you can see Eita is going to be an absolutely enormous device. It's currently being built in the south of France in a place called Cadarache, because physicists aren't stupid. They like sunny holidays, okay? But it's a global endeavor. And the reason why fusion takes so long is because a project like this has involved pretty much most of the world. There are many, many countries involved. The piece of paper that was signed that said we're going to do something like Eita was in 1985 by Reagan and Gorbachev. Okay, so this is why this stuff takes so long. And it's not even built yet, but we're hoping that first light in this plasma will be around 2025, something like that. And the idea with Eita is that it will produce net energy for 400 seconds, which is really exciting. It's about half a gigawatt of power for about 400 seconds, which is an extreme step up from what we've seen at JET. And not only will they do that, they will also be testing out the kind of wall situation. So can we use lithium to generate more tritium? Will this stuff survive? What else? Robotics, remote handling, all of the things that you need that will make a reactor work. So it's a really interesting time as well, because Eita is a project that's being delivered by industry. So it's the first time industry have got on board with fusion in a really big way, because it can't be built like people like me at universities. It has to be built by big engineering firms that are used to building things like nuclear subs and so forth. And because it's unprecedented, no one's ever built a site that's regulated for fusion. We know how to do fission. It's actually a lot more tricky than getting the site regulated for fusion, because the safety requirements are different. So there's just been so many things that we've been learning with this pioneering project. So it's really, really exciting stuff that's happening right now. So we're in a really interesting time, right? So we've got JET at the moment, but we've got a whole load of other devices as well. This seems like quite a linear thing, but actually there are many, many different devices around the world telling us different bits of the fusion jigsaw puzzle that we have right now. Then we've got this next step device called Eita being built, which should be operational from beyond 2025. Also, we have the National Ignition Facility as well with the lasers, which in the next 5 years or so, I think you'll see really, really interesting results, if not ignition, but very, very close to ignition, which is a really exciting time. And there's lots of technology that needs to be developed as well in order to go from what we've got a sort of lab-based endeavor to basically a demo fusion reactor. And what we're hoping comes after Eita is something called demo, which is a demonstration fusion reactor, which we're looking at sort of, mid this century. So I think that commercial fusion will probably not be available till the latter part of this century, but that's just going through the sort of conventional linear kind of tokamak now, tokamak Eita, and then demo in the future. We're now seeing a whole generation of smaller agile devices that are coming online. There's been a big investment in what we call a spherical aspect tokamak, which is at Culham called MAST. There's been a big investment in a new project called STEP, which is going to basically, but this is in the UK, right? It's £220 million have been invested in trying to make new small tokamaks, which use high magnetic fields to overcome these losses rather than sort of going up in size. So there's lots of opportunity in sort of home turf in terms of the UK programme, in terms of this STEP programme. But also around the world, there are about 40 private companies now investigating all sorts of different types of fusion. So it might be that whilst we're on this sort of linear path from JET through to Eita through to demo, that there are all these other private ventures and smaller ventures that might deliver a reactor on a much more aggressive and much quicker timescale. So it's really interesting right now. So I want to leave you on a positive note that there's lots of opportunities in fusion right now, and it's a really exciting time. So thanks for listening, and my apologies again for the technical delays. Thank you so much.
So Kate, thank you so much for that fantastic talk. I started off by talking about the relevance of research in our daily lives, and I think you really amply proved that the work you do has such huge resonance in terms of the challenges that we face in terms of environmental sustainability, the desire for clean energy, if not cheap energy. So we've got a series of questions that I'm going to go through, some of which are kind of sequenced in an interesting way. So you've really addressed the timescale issue, which oddly enough was the first question to pop into. But let me ask a slightly different question. Do you feel, so the question was essentially the timelines for developing a commercial fusion power station. Do you feel that your expectations around the timescales that you talked about have been in any way threatened by the kind of the intersection between investment in science and the political situations around large economies getting quite antsy with each other? Is there the, do you think there are opportunities in a post-COVID world either to accelerate investment, where a number of, and particularly some members of the current government have been talking about DARPA levels of really large-scale investment, or on the other hand, are the issues that you've talked about in relation to Eita under threat because of geopolitical situations that you're worried about those levels of close collaboration going forward?
So that's actually a really interesting question. So so if you'd asked me 2 months ago what I thought the main problems were facing us, it would have been Brexit, right? Because obviously Eita is a European project of which we're a partner. Well, it's not a European project, it's a global project. And we have access through the EU into that project, right? So we are having to kind of withdraw from Euratom and back in order to contribute to Eita, because obviously, as you can see, we have expertise in a big way in the UK because we are housing JET. So the expertise that we've gained from JET and being able to do deuterium and tritium fusion there is needed in Eita. So we need to be part of that. Now, do I think that will affect the political will to make fusion happen? No, I don't think so. I think that it sort of cuts across I mean, the desire of all the partner countries, for example, in Eita, to make fusion work is great. There are various countries that have kind of, I think the country that have flipped in and out the most is America, because it's kind of dependent on the administration, right? But I think there's a big commitment of the majority. One of the reasons why I love being a physicist is because regardless of what's happening in the world, there will always be us physicists meddling around in the background working together. And actually, it's really nice if you think about the invention of the tokamak was actually in Russia during the Cold War. Scientists from Culham in the UK went out there through the Iron Curtain to talk with those, to understand what they'd done. And, you know, the political situation was almost irrelevant to them. Physics kind of cuts through all of that. Now, that being said, I think because of some very successful lobbying and also kind of the insecurities around Brexit and so forth, the current government have made an enormous commitment to fusion in the UK through the STEP project. It's pounds. That's a big deal. I mean, it's small fry compared to, you know, building an actual reactor. But the point is, this project will mean that we could, on an aggressive timescale, get a prototype reactor based on this kind of small technology, which is really, really exciting. And then, of course, you've got these private companies, which 5 years ago, that just wasn't a thing. That's really become a much bigger now. There's lots of investment going into these small companies with really interesting approaches. So, and I'm really pro that. I think that that's keeping a lot of intelligent people employed and kind of getting their expertise in the mix. And in fact, I think because of the nature of what they do, they're able to try these more high risk, high reward kind of approaches because they're not spending money from the public purse, let's say, right? So they can be a bit more kind of jazzy about what they're doing in terms of their approaches to fusion.
So that segues rather beautifully into a question posed by Richard O'Donnell, which, and I'll read it directly to you. Talking about fusion energy would not be cheap at first, but one of our main, perhaps naive hopes for uncovering a boundless energy source to make its benefits available to poor nations and poor people worldwide. So I guess there is, again, the challenge around once the technical difficulties are resolved and the energy can be actually produced and packaged efficiently, will the kind of intersection again with political willpower, but perhaps also that level of private sector investment. If private sector is getting involved, they generally wish to have some form of return on investment that might be required a lot faster than the timescales you were talking about. How do we ensure an integrity of the ability to democratize the availability of clean energy in the way that you've been talking about?
So that's a really good question. And I don't know if I can necessarily answer that exactly. However, for example, Eita raised a piece of paper that said we might do something like Eita was signed by Gorbachev and Reagan in 1985. You know, I was 6 at the time, right? So, and it's taken this kind of long period of time to draw this stuff together because it's a global project. There are people all over the world. So whilst it's kind of tedious in its timescale, what it's done is it's cut up the technology like a Terry's chocolate orange, and each nation is making a different part. So no around that. So that's kind of one of the most unique and beautiful things about the Eita project is it is a kind of global effort there. Water is pretty much available in most countries. Obviously, there are some landlocked countries. What we need is seawater to get the deuterium, right? And so it should be much more democratized in terms of the fuel rather than just relying on these big nations that have access to like fossil fuels, for example, which tend to make their like a lot more sort of geopolitical instability. Now, the biggest cost of fusion is the capital outlay. It's not the fuel. The fuel doesn't drive the cost of fusion. It's the capital outlay, which in order to set the thing up in the first place, and also the lifetime and then decommissioning eventually, because ultimately there will still be, because the neutrons do activate the material, so there will be some waste, but not from a fission reactor. So it needs to be made competitive. But I think if you look at the market now, it wouldn't really be. But the thing is, I think the markets are going to have to change massively going forward. We don't know that the energy markets in 20 years are going to look like what they do now anyway. So it's hard to say what the future's going to hold in terms of that. So,
well, that's certainly true at the moment. Some science questions coming up, which I'm not going to reinterpret. Somebody in the audience wants to know, is there a way of combining the inertial confinement method and the magnetic confinement method together?
That's really interesting. Not directly, but there is investigations going on at the Rochester lab. They're inertial confinement fusion, but they're trying to use magnetic fields to actually try and change some of the physics going on inside there to make it a more efficient reaction. So whilst I can combine lasers and tokamaks, we are using magnetic fields to try and improve the situation in terms of inertial confinement fusion. So that's really, really exciting.
Okay, so somebody else wants to know, is there any possibility for cold fusion in the future?
I genuinely wish I had £1 for every time somebody asked me that question.
Even I've heard that question before.
I would give all of that money back into fusion, but obviously I wouldn't just put it in my pocket. So cold fusion is an interesting one, right? Because obviously if we could do that, then it would solve a lot of the problems, because you're not dealing with matter that's heated to very, very high temperatures. The issue is the physics kind of doesn't stack up, right? Because you've got to heat matter to really high temperatures in order that you overcome this, what we call Coulomb repulsion between two particles. So they're two, say you've got two positively charged particles, they don't want to be brought together. The force that they feel between them, the Coulomb force, is resistive, right? So it's repulsive force. But as soon as they get close enough, basically the force that takes over is what's called the strong nuclear force. And all of the protons and neutrons in the nucleus are held together by this, but it's in a very, very short range force. So the particles have to get close enough so that the strong nuclear force takes over. You just need to at it in order to get that to happen. Now, that's not being said that you couldn't lower this kind of, you can do something called muon catalyzed fusion, for example, which instead of having electrons swimming around, you have muons, but it's not very energetically favorable. And then you've got the experiments that happened, like the Pons and Fleischmann experiment, the famous one that could reproduce. And this is the point. It would be fantastic if everybody got let in, could see what these people were doing, and could try and reproduce it in a public way. But the problem is there's a lot of reluctance to share the experimental details. And so we can't tell whether these things are real or not, or whether they're reproducible or not. And that's a fundamental tenet of science. That person did and get the same result. And the problem is no one could do it, which means we don't think that the experiments were valid, right? That's just the way science works. Now, I don't like to, poo-poo people's work. Really, cold fusion is not going to work. So we should stop worrying about that.
So actually, I'm going to skip down because there's sort of a neat segue into somebody has asked, what accidental scientific openings do you have hopes for along the fusion research path? Neutron sources, high intensity laser pulses, or something different?
Yeah, so that's one of the things, right, that means that big physics projects, so for example, if you think about the LHC, right, it's this large hadron collider that's at CERN, right? It discovered the Higgs boson. The Higgs is such an intangible thing. Why would anyone care about the particle that, confers mass in the universe, whatever? But the point is, lots of things happened, one of which was the development of the World Wide Web, right? So that's a big, big thing, right? So there are many different things, probably infinite technologies that are being developed that will support fusion, but also support a number of different areas. So for example, in my area of work, so the laser driven fusion, the lasers that we have at the moment, so the NIF, for example, is a big laser, but it only fires a few times a day. And if we want to make fusion into a power station through lasers, it would need to fire 10 times a second. So we need to develop lasers that will fire high energy, but also high rep rate. But those lasers can also be used to form the highest intensity lasers in the world, which can unlock the secrets of the universe, such as things like quantum electrodynamics, i.e. you can fire a laser into a vacuum and get something, right? You get something from nothing. It's called boiling the vacuum. So there's the kind of fundamental physics parts, but then there's all the kind of laser and optical technology that you develop that can be used for a whole range of other things. And there are stories like that to be told everywhere. We've got a beautiful story actually from the Plasma Institute, where we've got these array of microwave detectors that can be used to look at the microwaves emitted from the tokamak, because plasmas emit in the full spectrum, right? So you've got plasmas emitting microwaves, and then you can measure them using this special detectors to understand what's going on inside the tokamak. And that technology and the back end of that technology, the acquisition of that data, has been transferred to a company called Silotech, which is just at the edge of the moors. And they're using it to try and understand how to detect tumors, for example. So, you can take this one sort of microwave technology and then transfer it to a private company and help them do something where they can develop a medical device, for example. So, and that's an area that they've not actually worked in before as well. So we're helping them unlock a whole new market. So fusion has the potential to do that all over.
Brilliant. So a couple of questions related to each other around prioritization. In a kind of world of scarce resources and getting rapidly economically potentially scarcer, in the future, how do you prioritize a kind of balanced portfolio of investment in really fundamental research, such as fusion, that the questioner has described as ambitious, but perhaps more hypothetical? They have a view on that, relative to the implementation of more conventional renewables, photovoltaics, on and offshore energy sources, wind. And part of that as well, then, somebody else has kind of tuned in to say, will the development of renewable energy, especially offshore wind, solar, thermal, PV, hydro, wave power, render the kind of nuclear technologies, the investment in fusion, I think I know what your answer might be, less important in the future? So I guess it's a kind of balancing question of, by shoveling lots of investment in very long-term science, are we missing opportunities to address a clean energy question now? And how would you defend? You're going before HM Treasury or the European Union or DARPA. Tell us your pitch about why you need more investment.
Well, so I think the general view, before I get onto kind of money specifics, is that you need a broad portfolio of energy generation mechanisms, right? That is fundamental. And also the way that we generate energy and where we generate energy might be distributed far more than it is now. We at the moment, which is, it's changing, but we had all these coal power stations up the M1, it was very, very kind of centralized in various different places. We might see a much more distributed and localized network of various different energy generation mechanisms, and renewables are an absolutely fundamental part of that, no doubt, right? I'm absolutely pro that. But the problem is we have a storage issue. And I said that we need reliable source of energy. We need to be able to bring it on and off on demand. And sometimes the wind doesn't blow, sometimes the sun doesn't shine. We need to be able to store that energy, and the storage technology is not there yet. It may be in the future, but at the moment it's not, right? So we need our tech bros like Elon Musk or whatever to actually work on it and get it right. But the point is, we do need a kind of big baseline energy source, which will provide a good baseline for the grid, a reliable source that when all else fails, we've got this, we can bring it on to cope with demand and bring it off again. And fusion does represent that. So that's why we'd need an energy source like that, which provides a good analog to the kind of current power stations that we have now of the kind of gigawatt level. So yeah, so that, but in terms of the money thing, just to say that, if you look at the funding profile of what you would need to get fusion to work, right, there's a kind of funding profile. We're on the funding profile that should have ensured no progress at all. Before STEP came online, we were on a funding envelope in the UK that would have ensured no progress. The fact is, physicists are really good at doing something for nothing, right? Which, to our detriment. Now there's a lot of opportunity, but even if you think about what 200 million is to the Treasury, that's loose change, right? Because if you think about, I want to get political, but what was spent, for example, bailing out the banks, or what was spent in Afghanistan is about 15 billion, right? So money is there. There are magic money trees when it is required. It just depends on what your priorities are. And I think clean energy is something that is so important to the future of not just this country but the world, that it's worth the investment, I think. But yeah, so we'll see.
Well, that feels like a very, very good place to kind of sign off. Apologies again to everybody. It feels very odd. Kate and I can see each other, but we can't see any of you. So we hope you've had a really, really good time. Yeah. We will be sending all ticket holders a link to our YouTube channel so you can catch up on this again and share it among your friends. Really also want to invite you to carry on engaging with us on our online events, and also to take note that the York Festival of Ideas, which is a really big part of our public engagement that Kate's spoken at many times, is also coming live to you from the 2nd of June, and we'll be launching the programme next week. So do keep an eye out on all our Twitter feeds for all of that. But again, I am lost in awe at not only the complexity and the sheer mind-boggling nature of the work that Kate does, but also her fantastic gift at communicating it so utterly brilliantly. I'm not sure that I have ever encountered a description of her work quite in the way of the chocolate, the Terry's chocolate orange, and that will live with me for some time to come. So thank you everybody for tuning in tonight. Please tell everybody, and we will ensure that we have all our Wi-Fi signals much stronger the next time. And thank you again from the University of York, and thank you to the wonderful Kate Lancaster and the York Plasma Institute. Thank you all, and good night, and stay well.